Hi, this is Subspace Embeddings under Nonlinear Transformations. I'm Aarshvi, and this is my work with my advisor, Professor Cameron Musco at UMass Amherst. So, in this work, we're studying how we can embed sets which are similar to the output of a generative neural network. So, consider the neural network in the figure. It takes a k-dimensional input and gives n-dimensional output. N is greater than k, very much greater than k. So it is clear that WZ lies in the k-dimensional column span of W. However, when the activation function f is applied to WZ, what can be said about the set of all possible outputs of the neural network? So the question we're looking into is, can we randomly project the set to a lower dimension such that each vector has its norm approximately preserved? So this problem extends to the general problem of embedding the output of a neural network. This has applications to in approximation algorithms, in compressed sensing, um, also in cases where sparsity constraints have been replaced by structural assumptions which come from generative neural networks. So formally, the problem that we're looking into is to give a low distortion embedding of sets S, which are formed by entrywise nonlinearity applied to a low dimensional subspace. The nonlinearity that we are considering is a typical activation function. So what is a low distortion embedding? We have a set of points in an n-dimensional space, which are projected to an m-dimensional space by an embedding matrix. Such a matrix is called an epsilon 1, epsilon 2 error embedding if it preserves the norms which are multiplicative in terms of epsilon and additive in terms of epsilon 2. Um, so when epsilon 2 is 0, this embedding is called relative error embedding. And when epsilon 1 or epsilon 2 are not 0, we call it as additive error embedding. So what happens when our set S is the low dimensional subspace Z? That means what happens when the function is identity. So it is well known that a random Gaussian matrix can embed the set S into order k by epsilon square dimensions. Such an embedding is called as an Oblivious subspace embedding. These results are really attractive. However, they only apply to linear subspaces. Um, when the sets have nonlinearities, OSEs cannot be applied. This arises from the finiteness of approximation using epsilon nets, which gets tricky when nonlinearities come into the picture. So there have been limited theoretical results for embedding nonlinear sets. This was one of the major motivation behind which we wanted to study this problem. So previously, there has been work done similar problem on a similar problem by Bora et al. In 2017. They show that a random Gaussian matrix is a low distortion embedding of S. Such an embedding is a relative error embedding when F is piecewise linear, and it is an additive error embedding when F is any L-Lipschitz function. However, the input is bounded in a ball of radius R. So in this paper, we give additive error embeddings for nonlinearities like sigmoid, soft class Gaussian. We also give relative error embeddings for nonlinearities like tan H, soft sign. Um, we further also give applications to compressed sensing. Overall, we build initial steps for understanding how sets like S can be embedded oblivious to the data. So this is an overview of our results and the results in the previous work. As we can see, the 2017 paper shows that any L-Lipschitz function can be embedded into dimensions which depend on the Lipschitzness. However, there's a constraint that the input is bounded in a radius R, and the dimension also depends on that. We give additive error embeddings for a class of nonlinearities without the bounded input assumption. In case of relative error embeddings, the previous work is giving relative error embeddings for functions which are piecewise linear. We give relative error embeddings for functions which for a general class of functions which are like tan h, arctans of sine. We look into the details of the class of functions that follow our nonlinearities in the next slides. So let's go into one of the main results of our work. Um, we show that with high probability, a random Gaussian matrix is the additive error embedding of S if the function satisfies the following constraints. First is that if the function has if the maximum double derivative of the function is bounded, and the second is that if the function has linear asymptotes. So, for instance, that would be something like a sigmoid which has constant asymptotes and the double derivative is bounded. For functions which satisfies the constraint in the previous theorem, as well as are close to linear near the origin, we give relative error embeddings. So, relative error embeddings so example would be something like a tan h, which also has asymptotes, constant asymptotes, and is close to linear near the origin. To visualize the examples, one example for additive error would be something like soft plus, in which case the function is the double derivative is bounded, and we can see the asymptotes. In case of relative error embeddings, an example would be exponential linear unit, which is linear beyond like when x is greater than 0 and has a nonlinearity when x is less than 0. So it can be seen that ELU is approximately linear near the origin. This is why it can be embedded using relative error embeddings. So let's get into the overview of the way we have proved our theorem. So we know that the functions into consideration have linear asymptotes. Um, so we approximate the function using a piecewise linear approximation. The error of such an approximation is bounded using Rolle's theorem. Rolle's theorem, the error of approximation of Rolle's theorem depends on the number of pieces or the interval and on the supremum of the second derivative. So that makes it clear where our two conditions for additive error embeddings come from. Now that we have the number of pieces of approximation with a good error, um, we applying that to each vector in the set, we can see that the set S can now be approximated using by another set which by a space which consists of um, a union of fragmented linear subspaces. Um, so S can basically be partitioned into order if there are p pieces of approximation. S can be partitioned into p and into the k linear subspaces. Now that we have so many linear subspaces, it is obvious that we'll be applying Oblivious subspace embedding. So we apply OSE to each space and we take a union bound over all the subspaces. And this completes the proof of additive error embeddings. It can be seen that in case of sigmoid, the region between the purple lines is approximated using a piecewise linear function, and beyond the purple lines, we know that it is an asymptote, so it's close to linear. In case of relative error embeddings, we split the set into vectors which have smaller norm and vectors which have larger norm. We use the property that vectors which have small of the function to be close to origin to prove relative error embeddings for those functions. So some of the open directions in our work are, the first one is deeper networks. We were successfully able to embed sets which are like the output of a two-layer neural network. However, as the depth increases, the number of pieces of approximation as well as the error blows up. So that's one thing which is an open problem. A second problem into consideration is the extension of a class of nonlinearities, which can be embedded. So one promising result is Gordon's theorem, which shows that the embedding dimension for any set depends on the Gaussian mean width. So if we somehow are able to obtain the a bound on the Gaussian mean width of the set S, so same can be said about the dimension. Um, the another direction that we're working on currently is to extend the piecewise linear approximation to polynomials. Um, in case of polynomials, we are expressing polynomials as a tensor product, and thus results from Haupt et al. In 2017 are useful for sketching tensor regression problems. Okay, so thank you.